second order or higher order system. When I say higher order, as far as gate point of view is concerned, our scope is concerned, we are going to deal with second order systems in detail only, right? So starting with the definition, as we wrote the definition of a first order system, disturbance past is same, response system पढ़ने के बाद ही discuss कर सकते हैं. So now we have to model the second order system. Now please note that I told you that the mass capacity system and the energy capacity system, when you take the mass capacity and energy capacity system, they generally give a first order differential equation when we model them. So they can be easily modeled with the help of first order differential equation. As a chemical engineer, we are more comfortable, we are more, we can say, we have a habit of writing mass and energy balance equations, right? But as far as second order systems are concerned, what was the third type of equation? Conservation of momentum. When you write momentum balance equation, that is the Newton's second law, on any system, in that case, we obtain a second order differential equation. So force balance or momentum balance, generally we don't discuss much of momentum balance in our scope of chemical engineering. So if the discussion or modeling of systems is concerned, first order modeling, first order system modeling is more important. Its analysis is more important. Its analysis should be more detailed. Important तो ये भी है, गेट में यहाँ से भी क्वेश्चन आ सकता है, बट इसकी डिटेल्ड एनालिसिस नहीं करनी है. So I am not going to take 5 or 6 or 7 models like we did in the case of first order system. Are you getting the reason? Reason being here, it's the momentum balance, and there it was mass and energy balance. Fine. And we are, as a chemical engineer, we are having a characteristics that we know how to write mass and energy balance, and we know less about momentum balance. मैं नहीं कह रहा कि नहीं आता या नहीं आना चाहिए definitely, but modeling जिन systems की करनी है, generally they will be mass or energy capacity systems. Fine. So let us first write the definition. So I was giving the justification that why we will not discuss the second order systems modeling in detail. I mean, I'm not going to take 3-4 examples here. Fine. Right. So what is the definition? A system or process whose dynamics can be described. Dynamics means response or behavior. You can use various kind of words here, whose dynamics can be described by or described with a second order differential equation. Second order differential equation is called a second order system. It's called a second order system. Okay? So that was the definition of second order system. So generally, when you write conservation of momentum, it is a second order system. I'll come to the type of second order system. Before that, let us write the standard form of equation. So standard form of second order differential equation will be A naught d square y by dt square. अभी देखते हैं कि सेकंड ऑर्डर सिस्टम कौन से होते हैं. फर्स्ट ऑर्डर के लिए आइडिया लग गया था ना, मास एंड एनर्जी कैपेसिटी सिस्टम. सो आई विल टॉक अबाउट वेरियस टाइप्स ऑफ सेकंड ऑर्डर सिस्टम, देन आई विल एक्सप्लेन इन डिटेल. राइट नाउ वी आर स्टार्टिंग फ्रॉम द सेम फैक्ट वेयर वी स्टार्टेड इन द केस ऑफ फर्स्ट ऑर्डर सिस्टम. वी स्टार्टेड विद द डिफरेंशियल इक्वेशन. डोंट वरी अबाउट दिस ए नॉट और A1 और A2, डजंट मैटर, आपको जो पसंद है वो लिखो. A1 dy by dt. Of course, here what is y? Y is the output variable. In case of control language, the variable in which we are interested is the output variable, right? ये अभी मैं आपको आगे समझाऊंगा what is input and output variables, but from now only you should be you should develop a habit that output variable is not necessarily the output stream coming out of the process. Output variable can be anything. It can be anything in which we are interested. It can be that variable which we are observing, right? Your objective, your aim, your system, the behavior, the response which we are analyzing, that is the output that is the output variable. It can be the liquid level, it can be the flow rate, it can be the temperature, it can be it can be the velocity, can be the position. Whatever you are analyzing, can be composition also. Whatever you are analyzing, that is the output variable. Fine. So y by dt square, A1 dy by dt. So y is a function of time, plus A2y is equal to b1 x. Of course, x is also a function of time, y is also a function of time, correct? X is the input variable, y is the output variable. Fine. Now, this is the standard second order differential equation. But if I ask you, apart from a second order differential equation, which words you will use to describe this kind of differential equation? ये मैं first order में भी कर सकता था. Just I got an idea of asking you कि इस differential equation को अगर मुझे describe करना हो, I mean I want to specify this type of differential equation, तो क्या बोलूंगा इसको? This is a second order, correct? Second order. What else? It is a differential equation, that is fine. It is second order. What else? What kind of differential equation? What extra attributes you can give to this differential equation? Extra attributes. और कुछ quality बताओ इसकी. Is it linear or non-linear? I told you the definition of linear differential equation and non-linear. उसको याद रखना. बहुत simple mathematical questions होते हैं, but students don't clearly understand the definition of a linear differential equation, so they make mistakes there. This one is a linear differential equation. Fine. So second order, linear. What else? It is ordinary or partial. One dependent variable, one independent variable. There is no other independent variable. So it is ordinary. सेकेंड ऑर्डर. आप पूछोगे सर फर्स्ट ऑर्डर में ऐसा नहीं था क्या? फर्स्ट ऑर्डर में भी था, ये ख्याल मुझे अभी आया, ठीक है ना? सेकेंड ऑर्डर लीनियर ऑर्डिनरी डिफरेंशियल इक्वेशन. और भी कुछ रह गया? डिफरेंशियल इक्वेशन. दैट्स इट? नो. विद कांस्टेंट कोएफिशिएंट्स, है ना? इन केस देखो होता क्या है, व्हाई आई एम टेलिंग दिस, when you are not sure about your knowledge, right, what you have studied, when you are not sure about it, तो कोई ऐसे ही छोटा मोटा चलता फिरता कोई भी आएगा और आपको परेशान करके चला जाएगा, right? If you are sure enough, if you are confident enough that you have prepared for the exam, you have prepared for the interview, right, then सामने वाला अगर आपको पूछेगा कुछ तो परेशान नहीं कर पाएगा. If you don't know, say don't know, no problem. But क्या होता है कि if you are not confident enough, देन अगर उसने थोड़ा सा डाउट क्रिएट कर दिया आपके माइंड में, देन यू विल स्टार्ट टू फील कि यार मैं तो कुछ पढ़ा नहीं है, तो शायद जो मैं सोच रहा हूँ शायद वो गलत है. ये डाउट क्रिएट किया जाता है इन द इंटरव्यूज ऑल्सो, राइट? वो पूछेंगे कि नहीं ना, कई बार बोलेंगे आप आंसर करोगे, बोलेंगे नहीं ये तो गलत है, ठीक है, क्या ऐसा नहीं होता? वो आपको मतलब डाउट में डालना चाहता है. दे नो दैट यू आर नॉट कॉन्फिडेंट अबाउट योर नॉलेज, राइट? इफ यू हैव स्टडीड द थिंग्स क्लियरली, यू शुड बी कॉन्फिडेंट अबाउट योर नॉलेज, राइट? वन ऑफ माई स्टूडेंट वॉज देयर. In the BARC interview, he faced this kind of situation, but he was pretty sure what he has read and what he don't know. ये भी मालूम होना चाहिए कि नहीं जानते. ऐसा नहीं कि वो आपको डाउट में डाले जा रहे हो और आप अपने इमेजिनेशन का यूज करके उनको आंसर कुछ भी दिए जा रहे हो. There is no meaning of doing that. Fine. So you should know whatever you have studied. You should know it कि exactly कितना पढ़ा है और क्या पढ़ा है. उसमें अगर आपको ज्यादा घुमाए फिर ऐसे ही सर we don't know, not a problem. That is not a problem, right? You don't have a particular information, just say it that you don't know. It will save your as well as their time, and it is always the best policy in the interview कि फालतू की बातें नहीं बतानी उनको. जहां पूछा to the point रहो, stick to the point. Okay, so second order linear ordinary differential equation with the constant coefficients. Fine, that is the a form of the differential equation when you model a second order system. What was the next step? Do you remember? You write this equation at steady state. d square yss by dt plus a1 dyss by dt, ठीक है ना? या प्लस a2 yss is equal to b1 xss. Clear? Then deviation variable अभी बना सकते हैं, ठीक है? बना लेते हैं deviation variable. It will be a naught d by dt d square by dt square, I'm sorry, here it will be dt square, d square by dt square y minus yss plus a1 d by dt of y minus yss plus a2 y minus yss. I am trying to introduce the deviation variable is equal to b1 x minus xss. What I am trying to do, you know, we started the first order system. I took the first order differential equation, then we derived the general equation, general transfer function of a first order system. Here also I am going to derive, पता होना चाहिए ना क्या करें, I am going to derive the जनरल सेकंड ऑर्डर ट्रांसफर फंक्शन. यही ट्रांसफर फंक्शन किसी भी सेकंड ऑर्डर सिस्टम के लिए चलेगा. ठीक है. सो लेट अस राइट दिस इन द फॉर्म ऑफ डेविएशन वेरिएबल. द इक्वेशन बिकम डी स्क्वायर बाय डी टी स्क्वायर कैपिटल वाई, है ना. दिस इज नाउ द डेविएशन वेरिएबल. ऑफ कोर्स वाई इज ऑल्सो फंक्शन ऑफ टाइम. प्लस a1 d capital Y by dt plus a2y is equal to b1 x. चलेगा. Now what was the next step? I told you that in which variable we are interested. We want to know the value of y. So I am going to make the coefficient of y is equal to 1 by dividing entire equation with the coefficient of y. So a0 a2 d square y by dt square plus a1 by a2. Don't try to learn these things. a0 by a2 is only the things. Try to learn this, that we always divide by the coefficient of y. It can be a2 in some books. In some books follow the notation a2, a1, a0. They follow this notation also, right? So a1 by a2 dy by dt plus y is equal to b1 by a2 x. Now what was the next step we did in the first order system? We gave names. इनको कुछ नाम देना है. This name was equal to tau p. So this is tau p. Fine. This name was equal to kp. This is kp. Correct. But there is a new term introduced here because this is a second order differential equation. We have a new name for this. This is called 2. अभी 2 कहाँ से आ गया? अब आ गया. ठीक है, इसको लिख लो 2. Then there is a word or symbol, you can say zeta. आप जैसे बनाना चाहें, बड़ा जीटा होता है और छोटा जीटा होता है. whatever the way you like, you can make this zeta. Again a Greek symbol, we call it zeta, right? I have a habit of making this zeta like this, 2 zeta tau p, right? This is the name given to this. Now I'll talk about कि इसको क्या बोलते हैं, इसको क्या बोलते हैं, but let us write the equation now. This is tau p d square y by dt square, tau p d square y by dt square plus 2 zeta. Don't worry about this. नहीं बन रहा, किसी तरह बना लो, है ना. आपको समझ आना चाहिए. That is, this is zeta. We are not giving subjective paper here. Plus y is equal to kp into x. Next step, take Laplace. And please understand that again we are working with deviation variable. So the value of all the deviation variable, the initial values of all the deviation variables are going to be 0. ठीक है. So tau p s square y bar s, rest terms will become 0. So I am not going to write s into capital Y of 0 minus s into minus y dash of 0. All those terms will be 0. I explained initially only. This will be s into y bar s, fine, plus y bar s. I'm taking Laplace now in this step. Kp into x bar s. What is the objective? To write the transfer function. Take things common from here. Y bar s by x bar s, which is the second order transfer function, gs is equal to, you have this relation as kp tau p square s square plus 2 zeta tau p s plus 1. This is the standard form of a second order differential equation, right? There are 3 parameters here. In first order, there was only kp and tau p. We have here kp, we have here tau p, we have here zeta. So first of all, names you must know. kp को यहाँ भी वही बोलते हैं जो पहले बोलते थे. kp is equal to steady state process gain. kp is equal to steady state process gain. ठीक है? Okay. Let me tell you one more thing. I told you how to find the gain of any system. Any system. I told you that method was valid for any system. Please recall. कैसे करते थे? सोचो अभी, सोचो. यही सोचना जरूरी है. जैसे ही मैंने आपसे सवाल पूछा या आपको खुद कोई डाउट आया, पहले एक बार सोचो कि करते कैसे थे. What was the method to find the gain? I'm not talking about delta output by delta input. That was the definition of gain. But by using that definition, I told you a method to find gain. And the final result in that method was just put s is equal to 0 in the transfer function. Right? And not in ys, not sys. I'm just talking about the transfer function. Put s is equal to 0. You're getting kp. That is the steady state gain. Fine. Steady state process gain. Same definitions are valid here. Tau p. Tau p is called time constant नहीं कहते इसको, है ना, टाइम कांस्टेंट लिख के इसको क्रॉस कर लेना। आई टोल्ड यू दैट टाइम कांस्टेंट की वो जो डेफिनेशन थी, ऑल दोज थिंग्स, उसको फर्स्ट ऑर्डर सिस्टम के साथ वहीं भूल जाओ, है ना। सम बुक्स राइट हाउएवर टाइम कांस्टेंट, बट दैट इज नॉट करेक्ट। द नेम ऑफ tau p in the second order system becomes natural period of oscillation. Natural period of oscillation. Why this name has been given and what is the significance of this name will come to know later. जैसे मैंने पहले आपको tau p का significance शुरू में नहीं बताया था, we discussed the significance of tau p once we made the response. Here also, once I draw the response, once I discuss about the response, तभी मैं tau p का significance आपको बताऊंगा, ठीक है। अभी significance के बारे में बातें नहीं करेंगे। So just write down the name. Zeta. Zeta is called, just learn the names, damping factor, damping coefficient, damping ratio, जो बोलना है बोल दीजिए, ठीक है। damping coefficient and damping ratio, सारे नाम इसी के हैं, zeta के, ठीक है। damping ratio. So first of all, name must be clear. This is the idea of a second order system: the differential equation, the transfer function, and the parameters. If you know these three parameters of a second order system, of course you can write the transfer function. But without knowing, suppose if you don't know zeta, I just provide you kp and tau p. You can't, you can't write the second order system transfer function. Fine. You can see here that in case of second order system, the denominator is having a highest power equal to s. समझ आ रही बात? The denominator is having highest power is equal to s. In the first order system, the denominator was having highest power is equal to, this is s square, sorry. In the first order system, the highest power was equal to s of the denominator. So you can say that order is something which is related to the highest power of the denominator. Fine. अगर आप third order की system का transfer function लिखोगे, the denominator will be having a highest degree of 3. S cube will be the highest power of s. Like that. This is the trend. Okay, third order, fourth order नहीं पढ़ना, but you must know these things. Okay, so pause करके note कर लेना, फिर आगे बढ़ते हैं। तो मैंने आपको ये बता दिया कि what will be the standard transfer function. Okay. Now, before going to the response or before going to the modeling, see, I'm not going to model anything. I told you, I'll just model one system to give you example, to give you the feel of the second order system. पता तो होना चाहिए ना कि है क्या ही, है ना? I'll just model one example. Fine. When we will discuss the type of second order system. But before discussing the type, let us also analyze let us also give some more insight into this transfer function. नोट करते रहना, सब कुछ बहुत इंपॉर्टेंट है, नोट्स बनाना है ना। Proper notes are very important for your preparations. The more you write, the more you learn. This I have learned this in my approximately total 10 years experience of learning and teaching all, because I'm learning also and I was teaching as well. So I have learned that the more you write, the better you learn. And writing means not just copying the things. In fact, copy करने से भी याद हो जाएगा, but it's better that you recall the facts and then you write on a blank paper. और कई बार बच्चे क्या करते हैं, I have seen many students, they have a small whiteboard in their room, a whiteboard of dimensions 2x4. That whiteboard they are using, they have to revise something. तो ऐसा है, कई बार पेपर में क्या होता है, कई बार suppose you want to write something in the paper, sometimes you feel lazy, right? कई बार आप सोचते हो यार कौन करे, छोड़ो, है ना, आपको नोट्स कौन निकाले, कौन देखे। तो many students what they do, they have a simple whiteboard, और whiteboard के अलावा there is one more, there is a chart. I'm not talking about that, I mean paper chart. That is a chart which is coated with a glossy finish is there. That can be used, and a marker you can use. आपको छोटा सा topic revise करना है, write all the formulas, graphs, theories, everything on that chart. Done. The more you write and then erase it, right? It will save paper as well. और ऐसा भी नहीं कि आपको बार-बार bundle बनाना पड़ेगा. You can do that also. If you are comfortable with your notes by writing in your notes, then it's okay. Okay, let us talk about some points here. See, I told you that in second order system, we will not discuss much detail. So in second order system, we will only discuss अभी मैं मॉडलिंग पे भी नहीं जा रहा. Let's wait for some time. We will only discuss the response of step input. The response of step input. ठीक है. सेकेंड ऑर्डर में बाकी इनपुट्स का रिस्पॉन्स इज नॉट एज इंपॉर्टेंट एज द इनपुट एज द रिस्पॉन्स ऑफ स्टेप इनपुट. दैट इज वन पॉइंट. आई टोल्ड यू दैट इन सेकेंड ऑर्डर सिस्टम मैं ज्यादा डिटेल में वैसे ही बात नहीं करूंगा. जो भी बात करूंगा उसमें भी मैं केवल स्टेप इनपुट का रिस्पॉन्स डिस्कस करूंगा. ऑफ कोर्स आई विल टेल यू अ लिटिल बिट अबाउट. आई एम नॉट गोइंग टू डिस्कस लाइक अ रैंप बिकॉज रैंप इनपुट taking Laplace inverse will become very complex. Even in the case of step input, it will be complex, right? So I'm going to discuss the response of step input only. Second order system step input का transfer function derive कर रहे थे, and the expression we got was yt is equal to mkp by s. Yt was equal to Laplace inverse of this. This was our expression, right? S multiplied by tau p square s square plus 2 zeta tau ps plus 1. This was the expression. Fine. Now if you use the concept of this partial fractions, then I will write this expression as mkp by s into tau p square s square plus 2 zeta tau ps plus 1 can be written as a by s plus b by tau p square s square plus 2 zeta tau ps plus 1. ठीक है. This like this I can write the partial fraction. Fine. Okay. Now if you break this partial fraction, this is a linear factor, but this one is a non-linear factor. When there is a non-linear factor, either you factorize this in linear factors. Okay. So to do that, I will write this equation as a by s. Before factorization, let us make the coefficient of s square is equal to 1 by taking tau p square common. So this becomes b by tau p. This is tau p square, it should be. So s square plus 2 zeta by tau ps divided by tau p square हो जाएगा ना, tau ps plus 1 by tau p square. Fine. This is the scenario. अब अगर इस इक्वेशन की बात करें, this is a quadratic equation. What are the roots? Use the basic method for finding the roots of a quadratic equation. The roots of the equation, I'll tell you why I am doing this. ये इस तरह से क्यों explain कर रहा वो देखते हैं, है ना. The roots of the equation s square plus 2 zeta by tau p into s plus 1 by tau p square are. So are s1 and s2. So what is s1 and what is s2? So s1 comma s2 will be equal to minus b, that is minus 2 zeta by tau p, that becomes minus b plus minus b square minus 4ac. And what is b square? B square is and divided by 2a will also be there, so I'll do that. Divided by 2a. What is b square? 4 zeta square by tau p square. Fine. B square minus 4 ac, so that becomes 4 by tau p square. Correct. So I can write this equation as I'm taking here tau p square common, so that tau p square is this. So, okay, so s1 s2 can be written as 4 can be taken out common, and then out of the square root it will become 2. 2 will be cancelled from everywhere. So that is minus zeta by tau p plus minus zeta square, root of zeta square, it should be root of zeta square minus 1. Tau p square will be common and then it will be divided by tau p. Chalega? I've just used the basic method of quadratic equation, right? So S1, S2, मुझे एक I think I don't know whether I made that mistake or not. अगर ऐसा हो तो आप एक correction कर लेना. In the differential equation, I was thinking about that. I think in the differential equation, I wrote the coefficient of d square y by dt square as tau p. If I wrote this as tau p, please write that as tau p square. है ना? I don't remember whether I made this mistake or not, but please be careful. आप check कर लो. अगर यहाँ पे tau p लिखा था, write that as the tau p square. Okay, fine. Let's come back to this. These are the square root of the. These are the linear factors of this quadratic equation, right? So can I write now the equation mkp by s into. This was just in case I made this mistake so that आप गलती ना लिखो ना. You have to be careful, and after this there are other terms also. Tau p square s square plus twice of zeta tau p s plus 1. This can be now written as a by s, which is one linear factor, a by s plus b by tau p square. I made the coefficient of s square is equal to 1, and then only I can write this equation as s minus s1 and s minus s2, right? S minus s1 and s minus s2, where what is s1 and s2? S1 and s2 I told you. Minus zeta by tau plus minus zeta square minus 1 by tau. And yes, you have to remember this, है ना? ये याद रखना है. हो सकता है कोई फॉर्मूला, कोई क्वेश्चन सॉल्व करने में इससे हेल्प मिल जाए. Now, the nature of yt. What was my objective? My objective was to find the response of a step input to a second order system. I told you that in step input, in second order system, दो बातें बताई मैंने आपको. एक तो बहुत ज्यादा मेहनत नहीं करेंगे मॉडलिंग करने के लिए, बिकॉज मॉडलिंग ऑफ फर्स्ट ऑर्डर सिस्टम, डिटेल्ड मॉडलिंग ऑफ फर्स्ट ऑर्डर सिस्टम इज मोर इंपॉर्टेंट. इन सेकंड ऑर्डर सिस्टम ज्यादा डेप्थ में नहीं जाना है मॉडलिंग के लिए, ठीक है. दूसरी बात, इन सेकंड ऑर्डर सिस्टम the transfer function, as you can see here, the transfer function of a second order system is more complex as compared to the transfer function of first order system. So when we are analyzing the response, step response को बस analyze करेंगे, and I'm not going to analyze other responses because ultimately it will be difficult to take Laplace inverse. What was the objective? The objective was to find yt. Now how to find yt? Yt will be equal to Laplace inverse of a by s plus Laplace inverse of b by tau p square s minus s1 s minus s2. Correct? Fine. Now see, s1 and s2 is this. Now yt depends upon nature of s1 and s2. Fine. Obviously, now if s1 is real, s2 is real, then inverse will be something else. If s1 and s2 are real, equal, unequal, if s1 and s2 are imaginary, so ultimately ho kya raha, what kind of response you will get, that depends upon the nature of s1 and s2, because s1 can be anything, right? You know here that s1 can be anything. It can be a real value, it can be imaginary value, and if it is a real value, you know that imaginary roots always occur in conjugate pairs, right? If it is a real value, it may be equal real values or unequal real values, correct? So depending upon yt depends upon the nature of an s1 and s2, whether they are real and equal. That is one scenario. Real and equal, or real and unequal, or imaginary conjugates. You know that imaginary roots always occur in pairs, है ना? Imaginary conjugates. So what is the nature of s1 and s2? Based on that, the Laplace inverse will be different and yt will be different. This was not the case in first order system. First order system में क्या था? Always whatever be the roots तो वहाँ fixed थे ना. What was the root of the first order system? If you see the transfer function, it was mkp by s and then tau p s plus 1. So both were linear. What were the roots? One root was s is equal to 0 and one root was tau p s plus 1 is equal to 0, means s is equal to minus 1 by tau p. Now minus 1 by tau p is always real. There was no doubt. But here we have a square root term. Due to this square root term, the nature of s1 and s2 can be anything out of this. And for this nature, yt will be different. This nature, yt will be different. This nature, yt will be different. You can see yourself, मैंने input नहीं बदला है. Input is still step input. But even in the case of step input, I have three conditions which is going to give me three different kinds of response. Right? So, write on the statement. For the same step input, the nature of the roots S1 and S2 may give different response. Step input, the nature of the roots S1 and S2 may give different responses in different cases. Now tell me that, okay, yt depends upon the nature of S1 and S2, right? And S1 and S2 depends upon the nature of this term. क्योंकि बाकी सब तो रियल ही है ना, केवल इसी की वजह से इमेजिनरी, कॉन्जुगेट्स, रियल इक्वल, रियल अनइक्वल, उस तरह की बातें आएंगी, राइट? द नेचर ऑफ S1 and S2, राइट डाउन. The nature of S1 and S2. So the nature of S1 and S2 depends upon this term. Depends upon the term root of zeta square minus 1. What is the result of this root of zeta square minus 1? That is going to decide the nature of S1 and S2. The nature of S1 and S2 is going to decide the nature of Laplace inverse. And the nature of Laplace inverse is going to decide the nature of yt. तो इस केस में we have a step input only. मैं input change नहीं कर रहा, but even in the step input, due to the presence of this term, I have three different cases and three different types of responses. तो पहले मुझे इसको इस हिसाब से classify करना पड़ेगा. And the result of this, and root zeta square minus 1 depends upon the value of zeta. यहां से बात निकल के आई कि zeta is going to decide that what will be the value of root of zeta square minus 1. Root of zeta square minus 1 is going to decide that what will be the value of S1 and S2. S1 and S2 is going to decide that what will be the Laplace inverse, and accordingly yt. So what are the different cases here? You can see, you know that the square root of a positive number is positive, right? And square root of 0 is 0, and square root of negative number is imaginary. Fine. So based on that, we have three classifications here. You can see yourself. अब ये कहानी अगर आप समझ गए हो तो आपको खुद पता लग जाएगा कि सर मैं कौन कौन से ग्रुप्स, कौन कौन सी कैटेगरीज बनाने वाला हूं. ठीक है, आगे बढ़ते हैं. ठीक है, सो आई एम नॉट टेकिंग Laplace इनवर्स हियर, लेकिन यहीं पे कुछ कैटेगरीज बना देते हैं अकॉर्डिंग टू दैट टर्म स्क्वायर रूट ऑफ जीटा स्क्वायर माइनस 1. You can write down if zeta is equal to, or zeta is greater than 1. You can see yourself, zeta is greater than 1, then root of zeta square minus 1 is, if zeta is greater than 1, zeta square will be greater than 1 again, and that this root of zeta square minus 1 is positive. Then what will be the scenario? If root of zeta square minus 1 will be positive, then S1 will be minus zeta by tau plus a positive quantity, and S2 will be minus zeta by tau minus a positive quantity. So both S1 and S2 are real, and they will be same or different because plus something and minus something. Real and different. That is case 1. Case 2 will be if zeta is equal to 1. तो ये 1 क्यों आया ये समझ आ रहा है ना? 1 is there because of that root of zeta square minus 1. If zeta is equal to 1, then root of zeta square minus 1 is equal to 0. Both in this case, if this entire term is 0, what are the roots? S1 and S2 will be minus zeta by tau plus 0 minus 0, means real but equal. Both S1 and S2 will be real and equal. ये बात समझ आई? And suppose if zeta is less than 1, you know that if zeta is less than 1, then zeta square will be less than 1. Zeta square minus 1 will be negative, and negative का square root कैसा होगा? Imaginary. So S1 and S2 we'll write here first about the root. Root of zeta square minus 1 will be imaginary. It will be negative, right? Zeta square minus 1 is positive. Okay, this will be imaginary. And S1 and S2, S1 and S2 will be imaginary pairs. ये समझ आया? And you know, the nature of S1 and S2 is going to affect the Laplace inverse and hence YT, imaginary pairs. Imaginary conjugate pairs. Fine. So that is why in second order system, even in step input, we have three cases: zeta greater than 1, zeta equal to 1 and zeta less than 1. And in these three cases, the YT value is different. ठीक है? ऐसा फर्स्ट ऑर्डर सिस्टम में नहीं था. फर्स्ट ऑर्डर में अगर आपने स्टेप इनपुट दिया, वी हैड ओनली वन रिस्पॉन्स. while in case of second order system, you are giving step input only, but because of the presence of this zeta, we may have different types of response for various categories. Right? Now write down a system or a second order system with zeta greater than 1. Now we have some important names for them. पहले अभी नाम समझ लेते हैं, इसका मतलब क्या है, we'll talk about that later. For a second order system, write down like this: if a second order system is having zeta greater than 1, then it is called over damped system. तो अभी के लिए बस नाम याद रखना है आपको, है ना, over damped system. Fine. If zeta is equal to 1, this kind of system is called critically damped system. And if zeta is less than 1, this kind of system is called under damped system. Right? Under damped system. Fine. So if a second order system is having this categories of zeta, we'll be having three categories of system, and each of them will be having different response. Input is same. Please remember, input को मैं change नहीं कर रहा. Even in the case of step input, I'm having three responses. Right? So that is why in second order system, step input को ही पूरा discuss करना is a big discussion, and we don't go for ramp or pulse or other kind of input. Fine. Okay. लिख लो पहले इसको. I'll erase this part. Okay. So before going to the response of the system, now we have introduced new terms here apart from Kp and tau p. New term here present, which is zeta here. Fine. Now the question arises. Okay, before going to the responses, before going to the comparison, आपने थोड़ा सा समझ लिया कि भाई differential equation कैसी बनेगी, transfer function कैसा आएगा, है ना? And I'm going to discuss step input only, and the step input will be discussed in three cases. Now let us take some examples that what are the types of second order system. And I told you that I'll not take 4 or 5 models, only one example I'm going to take. Okay. That is the most common example we take in case of the second order system. Write down next. Types of second order system. Types of second order system. First type is inherently second order system. Inherently second order system. What is the meaning of inherently second order system? These are the system whose inherent characteristics, वो मतलब अपने आप में second order system है, right? That is the inherent characteristics, right? And what are those systems which are categorized as inherently second order system? See, the systems whose modeling equation gives a second order differential equation. सेकेंड ऑर्डर डिफरेंशियल इक्वेशन आर इनहेरेंटली सेकेंड ऑर्डर। वो अपने आप, उसमें आपको कुछ करने की जरूरत नहीं पड़ी, इट्स देयर प्रॉपर्टी, it's their characteristics, it is their identification that they are inherently second order system. Fine, they are naturally kind of second order system. आपको कुछ होता है ना कुछ चीजों में, जैसे कुछ inherently का मतलब क्या हुआ, कुछ आपके पास ऐसी चीजें हैं जिनमें कोई गुण पहले से ही पाया जाता है, आपको उसमें एक्स्ट्रा ऐड करने की जरूरत नहीं है, राइट? इनहेरेंटली कहते हैं ना ऐसा, आप पैदा हुए थे उस क्वालिटी के साथ, दैट इज योर इनहेरेंट कैरेक्टरिस्टिक्स। आपने कहीं से सीखा नहीं, आपको किसी ने वैसा बनाया नहीं, दैट इज कॉल्ड इनहेरेंट कैरेक्टरिस्टिक्स। सो इनहेरेंटली सेकंड ऑर्डर सिस्टम मींस दो सिस्टम्स जिनमें आपको कुछ अलग से एफर्ट ना लगाना पड़े, कुछ जोड़ना ना पड़े, कुछ रिमूव ना करना पड़े, ऑलरेडी दे आर पोजेसिंग द सेकंड ऑर्डर डिफरेंशियल इक्वेशन मॉडलिंग, सेकंड ऑर्डर मॉडलिंग डिफरेंशियल इक्वेशन, राइट? एनी एग्जांपल्स? फॉर एग्जांपल, viscous damper. I will say that any system in which there are moving parts, that is categorized in the second order system, because moving parts का balance लिखने के लिए you have to write momentum balance, and whenever you write momentum balance it will give you a second order differential equation. So one is viscous damper, which is also called spring dashpot system. ये होता क्या है? See, in theory we discuss this viscous damper in a very simplified way, but if you ask me that in real life, sir, what is the meaning of viscous damper, have you seen, आपने कभी देखा, आप कभी दरवाजा खोलते हो तो दरवाजे के पीछे एक लगा होता है, एक डिवाइस which helps the door to close, होता है ना? आपने दरवाजा खोल दिया, एक छोटा सा डिवाइस लगा होगा, वो क्लोज करेगा उसको। Similarly in vehicles also, in your bikes there are suspensions. Suspension can be air suspensions, it can be liquid suspension, that is also an example of viscous damper, right? So those systems can represent the viscous damper more or less approximately. What else? U-tube manometer. U-tube manometer. U-tube manometer की आप मॉडलिंग करते हो, that is also going to give you a second order differential equation. The question arises कि सर क्या U-tube manometer की मॉडलिंग पढ़नी है? Because in some standard books, like I think in Kafner, you will find that there is a chapter dedicated to this U-tube manometer modeling. In other books also, no need to go through the modeling of U-tube manometer, but yes, you should know that it is a second order system. What else? Pneumatic valves. Valves are also categorized as inherently second order system. What else? Externally mounted level indicator. Externally mounted level indicator. Mounted level indicator. ये सारे नाम आपको बता रहा हूं, कई बार, एक बार 2016 में क्वेश्चन आया था, which of the following is a second order system, right? So U-tube manometer was one of the option. बाकी के ऑप्शन ऐसे थे कि आपको देख के ही पता लग जाता है कि these are first order system, right? So I'm not listing out all the possible second order system, but suppose in GATE exam if they are going to ask, वो इसमें से ही कोई एक आएगा. What else? Pressure transducer, or sometimes they write differential pressure transducer, वो भी चलेगा. Pressure transducer. Transducer is a common word, जनरल वर्ड, जो आपको कई सब्जेक्ट्स में कई जगह सुनने को मिल जाएगा. एंड वेरी सिंपल मीनिंग ऑफ ट्रांसड्यूसर, इट कन्वर्ट्स वन टाइप ऑफ सिग्नल टू अनदर टाइप ऑफ सिग्नल. ट्रांसड्यूसर का मतलब ये होता है कि वो एक तरह के सिग्नल को, विच कैन बी एनी काइंड ऑफ सिग्नल, कैन बी मैकेनिकल काइंड ऑफ सिग्नल, कैन बी प्रेशर सिग्नल, कैन बी इलेक्ट्रिकल सिग्नल, कन्वर्ट्स इनटू अनदर टाइप ऑफ सिग्नल्स, which can be electronic signals or pressure signals again, right? So these are called transducers. Fine. So viscous damper, U-tube manometer, pneumatic valve, externally mounted level indicator, and differential pressure transducers are certain examples of inherently second order system. Fine. So समझ रहे हो, inherent का मतलब है these are the system which already possess the characteristics of a second order system. It is also possible that another kind of second order system you can generate, and they are called synthetic or induced. Synthetic or induced. Synthetic or induced second order system. Fine. Synthetic or induced. अब सिंथेटिक का मतलब क्या है? होंगे तो ये भी सेकंड ऑर्डर, आप इनकी भी मॉडलिंग करोगे तो आपको जो इक्वेशन मिलेगी दैट विल बी अ सेकंड ऑर्डर इक्वेशन, बट यू हैव ऑब्टेन्ड दिस बाय कंबाइनिंग two first order system. Right down. Synthetic or induced second order system, you have here two categories actually. Let us write both. we write here, first of all, by combining two first order system in series. By combining two first order system in series. अभी समझ लो, if you combine two first order system in series, the overall order will be second order. If you combine three first order systems in series, the overall order will be third order, and like that. So for having a second order system, you can combine two first order system in series, and this will be a kind of synthetically man-made kind of, man-made khair ye bhi hai, but this is a synthetically created. This is not inherently second order. Because if you have corrected two components, the component is not having inherent property of second order system. That was actually a first order system, and you connected two first order system to make a second order system, right? So that is called induced or synthetic second order system. So by combining two first order systems in series, right? So it can be a mass capacity system with another mass capacity system in series. It will be a second order system. Energy capacity system, which was a first order, combined in series with energy capacity system, or it can be mass and energy capacity system combined in series. That is one example of synthetic second order system. The second example of synthetic second order system is a controller having first order dynamics controlling a first order process. Controlling a first order process is called second order system. ठीक है? Now I think आपको इसका भी ज्यादा आइडिया नहीं लगा होगा what is this actually. यहाँ पे मैं ये भी लिख सकता था that a controller controlling a system can be a second order process, but it is not always true. In some cases, if you have a process, you are adding a controller, the order is not changing. The order remains unchanged. But in some cases, with some specific kind of controller, the order may be second order, and that is also categorized as synthetic or induced second order system. So these are the types of second order system. First one is inherently, sometimes we may say that characteristic second order, inherently second order systems, and induced second order system. So एक से ज्यादा फर्स्ट ऑर्डर को सीरीज में कंबाइन करने पे जो सिस्टम बनेगा, that is called induced second order. However, all of them are second order, but induced second order and original, inherently second order. Fine. So that was the type of second order system. No need to do the modeling of any of this. Yes, I'll discuss a little bit about this one, and no need to do the modeling of this one. लिख लेना, इनकी modeling नहीं पढ़नी है. But yes, I am going to discuss the modeling of this spring dashpot system because it is theoretically simple to derive. And here only we will understand by the modeling of spring dashpot system that what is the significance of zeta in second order systems. Okay? So let us take an example. Write down modeling of, ये एक ही मॉडल पढ़ेंगे, ठीक है? अच्छा, ये गेट में कभी ये मॉडलिंग से सवाल नहीं आया है, बट पूछा जा सकता है. This is in our syllabus, right? So modeling of spring dashpot system. Spring dashpot system. What is spring dashpot system actually, which is also sometimes called as viscous damper? Actually, I'm not making the exact equipment here. I'm just making the representation. Spring dashpot system example, I told you, the shock absorbers in your bike, or the door closer, the automatic door closer which you see in daily life, they are an approximation. I mean, this viscous damper is an approximation of those actual devices. So मैं यहाँ real diagram नहीं बना रहा, I'm just making the approximations. What is that approximation? This is suppose a rigid surface. This is a rigid surface, and at bottom, this is a frictionless surface. Why frictionless surface? Again, this is an assumption for the simplification of the model. Friction, of course, in real life there are frictions. In surface also there will be friction. ठीक है? तो frictionless surface लेना सिस्टम की मॉडलिंग को क्या कर देता है? आसान कर देता है ना. फ्रिक्शन फोर्स को मुझे काउंट नहीं करना पड़ेगा. I can exclude the friction force in my modeling derivation, and my model will be simplified. Right? Suppose there is a body here having mass m. Now the shape of the body is not exactly like this, and the construction is also not exactly like this. Suppose this mass m body is resting on this frictionless surface. Mass m body is resting on the frictionless surface. Clear? This body is connected with the wall with the help of a spring. Spring is connected. Spring का काम क्या है? If motion is in this direction, spring will apply force in this direction. And I hope अगर आपको basics physics याद हो, spring force is written as minus kx, where k is the spring constant and x is the position, right? Similarly, there is one more thing here which is called the damper. Damper को कुछ इस तरह से denote कर रहे हैं. This is the damper. This is damper. What is the meaning of damper? In damper, you can assume कि ये जो यहाँ पे container सा बना हुआ, in this container there is some viscous fluid. This container contains viscous fluid. And what is the role of this viscous fluid? This viscous fluid opposes the motion of the body. भाई अगर आप viscous fluid भर दोगे and then there is some kind of constructions, don't think that कि सर ये construction exactly ऐसा होता है. But for derivation purpose, we are assuming simplified construction so that I can easily derive the formula. है ना? For deriving the formula, these are certain assumptions. I'm not saying कि आप shock absorbers या फिर door closer को देखोगे तो उसमें construction ऐसा रहेगा. है ना? They are complex constructions. उसको exactly model करना possible नहीं है ऐसे board पे, right? But here I am taking simplified model. The viscous damper is filled with a viscous fluid and the viscous fluid causes resistance to the motion, right? So spring is also causing resistance to the motion. Write down here, spring and viscous damper and viscous fluid present in the viscous damper is causing resistance to motion of the body. Resistance to motion of the body. Body को आप move करोगे, if the body moves in this direction, both the spring and the damper is going to apply force in the reverse direction to motion of the body. Fine? Right. Suppose that I consider that a force is applied here, which is the input variable. This is a kind of disturbance, you can say. This is a kind of disturbance, F, which is a function of time. A variable force is applied in this direction, right? The movement of the body in this direction, suppose this is kx, so I'm considering this as x, right? ये एक काम करते हैं, y मान लेते हैं, because ultimately my dependent variable, my output variable is y. If this is the direction y, then this will be ky. इसको y मान लेते हैं ना? Doesn't matter. You consider this direction as direction y. So the spring force applied on the body will be ky. What you can say about this viscous fluid, the force applied by the viscous fluid? First of all, this is your system. You are clear about the assumptions that the surface is frictionless. Fine. So no need to consider the friction forces acting on these wheels or on the body, right? So which balance we are going to write? We are going to write here the momentum balance, conservation of momentum. That rate of change of momentum is equal to net force acting on the system, right? So what is the rate of change of momentum? Conservation of momentum equation will be conservation of momentum. So this is an example where I am writing conservation of momentum. What is the conservation of momentum equation? Rate of change of momentum. Rate of change of momentum. Momentum is a quantity where direction must be specified. So rate of change of momentum in y direction, I'm talking about this direction. Rate of change of momentum in y direction is equal to mass into net force. So net force acting in the y direction, right? So I can write here is equal to net force acting in the y direction. That is the conservation of momentum equation. Net force acting in the y direction. ठीक है? Okay. So can you tell me what forces we have to consider here? First of all, let me ask you a question. Do I need to consider the gravitational force while writing the balance? Yeah, definitely gravitational force is a force, है ना? Or when I am writing the net force acting on the system, I should consider the gravitational force or not? See, if this direction is considered as the z direction, then there is no need to consider the gravitational force because the gravitational force is not acting along the y direction. When you are writing a momentum balance, then we should only consider that forces, those forces which are acting in the specific direction in which I am writing the momentum balance. तो momentum balance जिस direction में लिख रहा हूं उसी direction की forces को consider करूंगा. तो what are the forces acting in that direction? One force is this which is acting in the positive direction and other forces are this which is acting in the negative direction. Fine. ऐसा नहीं करना कि इस माइनस के वाई के बाद एक और माइनस लगा देना. माइनस के वाई ऑटोमेटिकली शोज दैट दिस फोर्स इज एक्टिंग इन दिस डायरेक्शन. फाइन. सो माइनस लगाने का मतलब ही है, ऐसा नहीं कि सर ये नेगेटिव में एक्ट करी तो माइनस ऑफ माइनस के वाई हो जाएगा. तो वाई इज दैट डायरेक्शन, माइनस के वाई इज दिस डायरेक्शन. सो हाउ टू राइट द बैलेंस? सपोज फर्स्ट ऑफ ऑल net force acting on the body will be mass of the body multiplied by acceleration. What is acceleration? Acceleration is dv by dt. And what is v? V is rate of change of position. So can I write acceleration will be d square y by dt square? ऐसा लिख सकते हैं ना भाई. What is acceleration? Acceleration is equal to change in velocity by change in time. So dv by dt. What is velocity? Change in position by change in time, right? So du by dt. So d by dt of du by dt, dy by dt, that becomes d square y by dt square. Now what about the forces? The positive force acting in this direction, the negative force acting in this direction. See, that is why मैंने इसको x नहीं लिया, है ना? अगर x लेता तो आपको confusion हो जाती है कि सर ये आपका input variable है कि output variable है. That direction is output variable. Fine. What about this viscous force? How to write the viscous force? Viscous force कैसे लिखेंगे? तो मैं अभी बस यहाँ पे ये लिख दे रहा हूँ viscous force. All of you have studied fluid mechanics, I guess, right? And in that case, viscous force is, you can calculate according to that Newton's law of viscosity, that tau is equal to minus mu d, which direction I should take. Suppose this direction is the direction z, right? If you consider this viscous damper here, a detailed diagram of the viscous damper, we have a fluid here and then there is this. This is our viscous damper. Fine, है ना? Fine. You know that in case of fluid viscosity, if the motion in this is in this direction, I mean the motion is taking place in this direction, right? The viscous force will be acting in this direction. Correct? You know that the viscous forces will be like this. They will be acting in this direction. Fine. No, when there is a flat plate and on the flat plate, this is the liquid flowing like this. Motion is taking place in this direction. At near the plate here, the viscous forces are maximum. And as you go away from this plate, the viscous forces decreases. And after that, the boundary layer gets finished and there are no viscous forces, no effective forces, right? So when you write this Newton's law of viscosity, what you write? Suppose if this is y direction and this is x direction, then you write tau is equal to minus mu du by dy, because the velocity is changing in y direction. The velocity is here 0 and the velocity, if you talk about the velocity profile, it was like this, hai na? If you remember, the velocity was 0 near the wall and in the y direction it was changing. So what is this direction? This is z direction. Here the velocity will be changing in this z direction due to the viscous forces. Fine. So I should write here velocity u divided by dz. Velocity u divided by dz. Chalega? And what is the force? Viscous force. Viscous force is this multiplied by area. Viscous force is equal to minus mu multiplied by area du by dz. Fine. I can approximate this as viscous force is equal to minus mu into a velocity और del u कर सकता हूं, del z कर सकता हूं, और I can write this as simply u by z. ऐसा कब कर सकता हूं that du by dz is equal to u by z? Think about this. You have studied fluid mechanics. U by z. Now what is z? Z is this distance. Z is the distance. है ना? Z is this distance. Clear? And what is u? What is u? Can I say that u is dy by dt? Fine. U is dy by dt. So I can write this as du by dz. I can write this as u by z, and then minus mu into a, right, divided by z, and I can write u as dy by dt. Fine. ऐसा लिख सकते हैं. I can call this entire term mu a by z as some constant, right? This can be treated as constant. This is equal to c star. ठीक है, इसको c star कर दिया, कोई दिक्कत तो नहीं है. So now I am able to write the viscous forces as, now the balance will be f of t minus ky minus viscous force, which is c star dy by dt is equal to m d square y by dt square. Now, if something is not clear in this portion, you need to revisit the section of this viscosity or Newton's law of viscosity of fluid mechanics. That is very basic section. I don't think कि मैंने यहाँ बहुत complex कुछ rules या complex laws use किए हैं, right? So, what is the equation? This is the modeling equation. Now, you can see yourself. If I try to write this equation in the standard form, m d square y by dt square plus c star dy by dt plus ky is equal to ft. This is a standard form of the second order differential equation. Fine. इसको मिटा देते हैं, right? आप बना लो इसको, या एक काम करते हैं यहाँ कंटिन्यू करते हैं, right? This is the standard form of the differential equation. What was the next step? Either you write this in the form of deviation variable, fine, or you first make the coefficient of the output variable, which is y, equal to 1. So the output variable coefficient has to be 1 here. So I will divide the entire equation by k. So this becomes m by k d square y by dt square plus c star by k into dy by dt plus y is equal to 1 by k multiplied by ft. Now this is in the standard form. Of course, I can write this in the form of deviation variable. So I can write m by k. मैं अभी डायरेक्ट लिख देता हूँ, d square capital Y. No need to write this steady state equation. Now you know all the things. C star by k d capital Y by dt plus capital Y is equal to 1 by k capital F of t. Now the things are present in the deviation form. Now no need to take Laplace. You know that what will be the result. I think I should write here. What is tau p then? This m by k is tau p square. Fine. M by k is tau p square. C star by k. C star by k is 2 zeta tau p and 1 by k is kp. Fine. And now you can see yourself that what is tau p? Tau p is equal to root of m by k. Can you calculate what is zeta? You know that 2 zeta tau p is equal to c star by k. So 2 zeta tau p is equal to c star by k. What is zeta? Zeta is equal to c star by k into 2 tau p. And what is tau p? So let us write this root of m by k, right? So this will be c star by k into 2, right? This will be root of m by k, right? So this will be root of k by m. Chalega? Fine. Okay, now this is equal to c star by 2 root of m into k. That is the value of zeta. Now, please note that this is not a universal formula of zeta. Zeta, I'm just trying to find out the value of zeta for this particular model. ये zeta का कोई universal formula नहीं है. and what is Kp? Kp is 1 by K. Kp is equal to 1 by K. Fine. So zeta is not having universal formula as C star by 2, because you know that in second order system, it's not only the viscous damper which is second order. There are various systems. If you model this U-tube manometer, you will be finding zeta as some combination of some parameters. If you model this valve, again you will be finding some zeta expression. So this expression is with respect to this model. Don't learn this formula. There's nothing to learn here. So why I derived this? You can see yourself that what is zeta? Zeta is consist of C star by 2 mk. So zeta is equal to C star by 2 root of mk. Correct? Now you can see yourself that what is zeta? Zeta is equal to C star. C star is equal to mu into A by Z. Right? So I can say that zeta is made up of what are the properties in zeta? Mu, K, M, A, etc. All these things are physical parameters, right? Mu is a physical parameter, K is a physical parameter, mass is a physical parameter, area, Z means this distance, right? Other K is there, K is the spring constant. You know that all these things are positive, they can never be negative. So zeta is made up of these things. Of course आप कह सकते हो कि सर हो सकता है किसी और मॉडल में zeta नेगेटिव हो जाए. No, zeta is always made up of some physical parameters which exist in reality. So zeta is made up of physical values, physical parameters which can never be negative. Which can never be negative. You can see yourself, zeta can never be negative here according to these values, right? So I can say that hence in reality zeta can never be negative. Fine. एक चीज ये याद रखनी है. What else? What is the significance of zeta in the second order system? Zeta is consisting of some terms mu, some terms K, and you know that mu, viscosity, and the spring constant, what they signify? They signify the resistance to motion. It means I can say that in other systems also आपको कुछ ऐसा ही मिलेगा. देखो zeta का significance पता करने के लिए, to find the significance of zeta, I took this model, and from this model whatever idea I'm getting, I'm generalizing that idea for zeta. तो ऐसा नहीं कि 10 मॉडल चेक करूंगा उसके बाद जनरलाइज करूंगा. I know that this is going to happen with zeta in each and every model. I'm not saying that the exact formula will be same, but there will be physical parameters, and all those physical parameters signify the resistance. It means in a second order system, zeta or the damping factor, the damping coefficient signifies resistance. मैं फिर से बता रहा हूं कि कंफ्यूज नहीं होना, ठीक है, कि सर ने बस एक ही बार जीटा का फॉर्मूला क्यों लिखवाया. इज इट द यूनिवर्सल फॉर्मूला ऑफ जीटा? नो, दिस इज जस्ट स्पेसिफिक टू दिस मॉडल, और ये याद भी नहीं करना. दिस वाज जस्ट टू राइट दीज 2 पॉइंट्स दैट व्हाट इज जीटा. जीटा को थोड़ा सा आइडिया देने के लिए कि जीटा किन चीजों से बना है एंड जीटा का फिजिकल सिग्निफिकेंस क्या है. तो आप देख रहे हो जीटा इज मेड अप ऑफ सम दोस क्वांटिटीज व्हिच कैन नेवर बी पॉजिटिव, व्हिच कैन नेवर बी नेगेटिव. So it means in reality, in real situations, zeta can never be negative. And zeta is made up of those quantities like viscosity, like spring constant, which are opposing the motion, which are resisting the motion. In other models also, zeta will be made up of such quantities which are opposing the motion. Like in valve, there is motion. In manometer, there is motion. Everywhere there is motion. Fine. So zeta is going to oppose that motion. It means in second order system, zeta signifies the resistance of the system. Right? आप resistance of the system भी add कर लो. Zeta signifies the resistance of the system. Fine. तो ये गेट में नहीं पूछा कभी कि what zeta signifies, because this resistance, ये केवल मेरा समझाने का तरीका है. That I am going to relate this resistance later. कि zeta ज्यादा हुआ, resistance ज्यादा हुआ, now this is going to happen. You won't find a question कि zeta signifies what? This, right? आने को आ सकता है. You should have this idea that zeta signifies the resistance present in the system. Kp और tau p, देखो Kp का मतलब अभी भी वही है, steady state gain. हाँ, tau p का मैंने आपको यहाँ पे एक different meaning बताया, that I will discuss later. Fine. This was all about the type of second order system. Then why we discuss 3 cases of step input only. So I gave you the explanation that why we have underdamped, overdamped, all those things, right? Now there is one more significance of zeta. We call it damping coefficient. So what is the meaning of damping? We'll discuss all these things in the upcoming lecture.